This is a video about some individual gas laws. We'll be talking about Boyle's law, Charles' law, and Avogadro's law. The first law we're going to talk about is Boyle's law. And Boyle's law was found by Robert Boyle, who is actually the son of the Earl of Cork. And so one of the things he did in his spare time was study gases. And what he found is that as the volume of a gas decreases, so basically as you're squeezing the gas, as you're making its volume smaller, the pressure of the gas is going to increase. And when that happens, the mathematical relationship looks something like this, that volume is proportional, so the symbol is proportional to 1 over the pressure. We've seen that kind of relationship before. This is the kind of relationship that we call inversely proportional. And again, inversely proportional just means as one goes up, the other one goes down. Now, when we look at it in containers like this, so we have these containers, and they look like little pistons. That just means that we can change their volume. So by moving the piston up and down, it's like a changeable volume container there. And in those containers, we have 12 gas particles, and each one of these has 12 in it. The difference between them is that the first one has a volume of 8 liters. The next one, we cut the volume in half. The next one, we cut the volume in half again. And what we see is that as we cut it in half, so as we cut the volume in half, the pressure goes up by 2. So the volume was multiplied by a half, but the pressure went up by 2. And so those are inversely proportional, but it's a linear relationship. When we're looking at kind of changing the conditions, looking at how the volume changes when we change the pressure, or how the pressure changes when we change the volume, we can use Boyle's law in this way here, where it's saying that the first pressure times the first volume is equal to the second pressure times the second volume. Now, to think about why this works, why pressure and volume are inversely proportional, we have to kind of think about what pressure means again. To kind of review what's happening in these containers, this container has 11 particles, this one also has 11 particles. And the difference between them is this one has twice the volume that this one does, so it has a bigger volume. All right, so let's look at what's happening in each one of the containers. Over here, we have the same container, so 8 liters and 4 liters, but here we only have 1 particle, and you can see that it's kind of bouncing around. Now remember, pressure is all these little forces added together and then divided by the area of the container. So when we think about pressure, like pounds per square inch, that's pounds per square inch. And we can increase pressure by either increasing the pounds, so increasing the forces, or we can increase the pressure by decreasing the area that force is spread over. So in this container, the same amount of pressure, or the same amount of force, is spread out over all this area. In this container, the collisions are spread out over that area. And there's actually more collisions in this area because the gas hits the walls more often. So in this case, the area, at least, is lower. And we know when area is lower, the pressure is going to go up. So that's how changing the volume of the container can change the pressure of the gas. Now again, when we're given initial conditions and final conditions, we can look at this relationship as P1V1 equals P2V2, where these guys are the initial values and these are the final values. And given 3 out of the 4, you should be able to calculate the 4th. Let's practice that. So I'm going to read this problem here, and as I go along, I'm going to kind of mark in the problem where different numbers, what variables they mean. And I suggest that you do this when you're doing problems just so that it's easy for you to visually see what variables you have and then what variables we're trying to find. And then we can fit them into an equation. Okay. At constant temperature, so temperature isn't going to be a part of this here, a sample of 6 liters. 6 liters would be a volume of nitrogen gas at 2.5 kilopascals. 2.5 kilopascals is a pressure. It's allowed to expand, so we know that the volume is going up until it reaches 9.5 liters. That's a new volume. So because I have 2 volumes here, I'm going to mark the initial one, and the one that it's moving to, the one that it changes to, as 2. And I'm going to go back and kind of mark my pressure here. I know because if this is my initial volume, the pressure that goes with it is also the initial pressure. So I have my V1 and my P1, and I have my V2. The question says, what is the new pressure? So I am looking for P2. Okay, so now I'm going to use an equation that has pressures and volumes in it. I'm going to use Boyle's law equation here. And I'm going to first rearrange it so that I have everything on one side and I just have P2 on the other. So I'm going to erase, and I'm going to divide both sides by V2. Those cancel out, and so I get P1 V1 over V2 equals P2. Now all I have to do is put my variables into that equation. All right, so let's see, my P1 was 2.5 kilopascals. My V1 was 6.0 liters. My volume 2 was my 9.5 liters. And when I put that into my calculator, I got 1.57. The liters cancels out, and I get kilopascals. Thinking about sig figs, let's see, this number had 2 sig figs. This one also had 2. This one had 2. I should mark this to 2. So this would be 1.6 kilopascals. Now again in this problem, we had an equation with 4 variables. We were given 3 out of the 4, and we calculated the 4th. This problem could have just as easily given us initial pressure and a volume, given us a second pressure, and asked us to calculate the volume instead. All right, let's go on to Charles' law. I think that Charles was a super interesting person because he, lived in kind of the late 1700s, early 1800s, and his job, or I guess maybe it was his hobby, he was a balloonist. Okay, so I don't know any balloonists, but I think that's a really interesting hobby. And I just imagine, when I heard that, I just imagine, like, if you're a balloonist, that's a pretty new technology to you in your life, and you probably died a horrible death of falling out of a balloon, like some kind of experiment gone wrong, right? That's how I kind of imagined his life ending, but that's not true at all. He actually lived to be quite old, and he actually died of, like, the flu. I looked it up. That was a little disappointing to learn. Okay, but while he was doing his ballooning thing, he also studied gases, and he actually isolated boron and did a lot of really scientific things. But one of his greatest contributions was figuring out the relationship between volume and temperature. He found that volume and temperature are proportional to each other. So that means as volume goes up, the temperature goes up. You might think about that in kind of like a slightly different way. You might think about it as if you raise the temperature of the gas, the volume will also raise. So that's really saying the same thing, just a little bit different there. Okay, so they are directly proportional. As one goes up, the other one goes up. And we can see some kind of data here. We have the temperature in Kelvin, and we have the volume. You can see when we double the temperature in Kelvin, we double the volume. We do it again, double the temperature, we're doubling the volume. So that is directly proportional. I want to point out that that's true only if you look at it in Kelvin. That relationship is not true when it's in Celsius, and that's because the Celsius scale isn't an absolute scale. 0 Celsius doesn't mean 0 energy. That only happens in the Kelvin scale. So because the Kelvin scale is an absolute scale and 0 Kelvin means 0 energy, it means that the volume is going to be proportional to the temperature. Okay, so say you're given a changing conditions problem, and by changing conditions, I mean that you're given an initial volume and an initial temperature, and then you know how you change the temperature, and you're trying to find the new volume. When you're looking at a changing conditions problem like that, you're going to need an equation that looks like this. And we can also rewrite this equation. Right now it has the volumes on top, but we could rewrite this equation with the volumes on the bottom. Okay, that might be convenient if we're trying to find a temperature. So having the temperature on top is convenient if you're trying to find temperature. Having the volume on top is convenient if you're trying to find volume. These two equations are exactly the same, and it's okay to do that algebraically to flip the equation as long as you flip both sides. So I flipped this one and I flipped this one. So now let's do a problem where we're practicing our Charles law calculations. And again, I'm going to go through the problem. I'm going to kind of point out the variables or the characteristics that were given here and how they're going to fit into the equation. Okay. At atmospheric pressure, a sample of O2 has a volume of 55 milliliters. All right, so this is going to be our volume 1. It's at 27 degrees Celsius. Anytime I see Celsius, I know that's a temperature, but I also know that I'm going to need to convert that to Kelvin. We can only do gas law equations in Kelvin. So I'm going to add 273.15 to that. When I do that, I get 300.15 Kelvin. The 27 is only to the ones place, so I'm going to make sure that I mark my Kelvin temperature also to the ones place. Okay. What volume will the oxygen gas occupy? So it looks like I'm trying to find volume if the temperature is decreased to 10 degrees. So again, this is a temperature, it's my temperature 2, but I need to convert it to Kelvin. So when I take that 10 and I add 273.15, I get 283.15. This is only accurate to the tens place, so I'm going to mark my temperature there to the tens place. All right, so now I'm going to use my V1 T1 equals V2 T2, and I'm looking for a volume, so the volume's on top there, that's really nice. And I'm going to rearrange that equation so that volume 2 is just on one side by itself. Right, to do that, I'm going to need to multiply this side by T2 and this side by T2. Those will cancel out, and I get T2 times V1 over T1 equals V2. All right, now it's just about putting in the variables that we calculated, or that we found in the problem. And so T2 is 283.15 to the ones place. Volume 1 was 55 milliliters. T1 was 300.15 Kelvin. And that was to the ones place. When I put that into my calculator, I got 51.88 milliliters because the kelvins cancel out. And for sig figs, let's see, this had 2, this had 2, this had 3. I'm going to do it to 2 sig figs. That would be 52 milliliters. Okay, so that's a little practice with Charles' law, which is the relationship between volume and temperature. Right, the last law that I want to go over in this video is Avogadro's law, and you can imagine that anything that has to do with Avogadro has to do with moles, and that's true. Avogadro's law tends to be one of the more straightforward gas laws for students to understand, and it's because it says that as the number of molecules increase, and we could also say as the number of moles of gas increases, the volume increases. So the more moles you have, the more volume it's going to take up. Those are directly proportional because as one goes up, the other one goes up. And so the equation looks a lot like Charles' law, where the volume is on one side, the moles is on the other. Remember, we could also rearrange this with the moles on top. Okay, so the calculations are going to be extremely similar to the ones that we did for Charles' law. All right, in this video, we touched on Boyle's law, which is the relationship between pressure and volume. We talked about Charles' law, which is the relationship between temperature and volume. And we touched on Avogadro's law, which is the relationship between moles and volume. If you'd like some practice with these types of problems for Boyle's law, in our course pack, you're going to use page 45, and you're going to do number 2 and 4. You could also use page 47 and do number 4, 5, and 6. For Charles' law, you're going to use page 45, number 1, 5, and 7, and page 47, number 1.